The other day we left, I was giving an example. Before I go there, let me just indicate this table that I skip. Essentially shows you the design speed for crest vertical curves. The computed side distance, we're going to talk a little bit more about this today. Based on that design speed, because on curves you don't have a constant grade. That's why we need to talk a little bit more about that. And then based on this information, they calculate a K value, which was, remember, the length divided by the algebraic difference of what you have here, L over A, where A is the algebraic difference in grades. And then they round that value for design. So this is what you will typically be using in practice. So there's one curve, one chart like this for crest, another one for sag vertical curves. They are basically the same thing except different numbers. And the other thing that I skipped the other day was this chart, which basically is how it's a chart that appears in the manual that simplifies all this. So this is something that you would have inside a program, or you would use it like this. So essentially with this, you can, for a given G2 and G1 that define the value of A, for that combination of values, and for a given design speed, for example, let's say I have a G1 is equal to 3 and G2 is equal to -5. I keep touching the screen without intention. So 3 minus -5 would be 8. So if you have a difference, algebraic difference in grade of 8, and you're designing a road for 80 kilometers per hour, then the minimum length of a curve would be around 210 meters. And then you can go select any value above that. That's how you would use this type of charts in practice. Okay. Or if you have a given length of curve, and for example, a different use would be, let's say I have a 300-meter curve, and I'm designing things for, I have a 300-meter curve, and let's say I have a 7% algebraic difference in grade. So for those conditions, I know I shouldn't be going above, those conditions is for a road that's designed for 90 kilometers per hour, no more, not much more than that. Okay, so I cannot have a road for 100 kilometers per hour. So there are different ways to use this. It's not a big deal. And then finally, the last thing I want to mention is that when we do the problems with equations, we have to figure out which set of equations we need to use. In this chart, they have simplified this. You see this line, this division line? That divides the two cases when you have the side distance less than the length of the curve, or when you have the side distance greater than the length of the curve. Okay, so these equations on this side are exact. Notice that in here, they're saying the theoretical equations, the equations that we're using when we solve the problems, will give you this, but they have simplified on this side of the chart to something like that, and they have further simplified. They put a minimum length of curve, because otherwise you end up like with a break. So there are some practical considerations here. And let me add one more. You notice this line that is dotted there. Anything below that is kind of problematic for something we have discussed before. For very high design speeds, you would have longer stopping side distances. And because of that, you will have to provide curves that are very long. And when you have very long curves, even if you're going from a positive to a negative grade or vice versa, what's going to happen is that on a long portion of the road, your grade is going to be near 0. So you may have problems with ponding of water in those situations. So that doesn't mean that you're not going to design curves like that, but you have to be extra careful to make sure that your slopes, your cross slopes are good enough to drain the water. So you have to pay special attention to that. So this is how you would use these things in practice, but I want to mention that before because you're going to see this chart. We're not going to be using it for the class, but it's something that you should know for your practice. Okay, so I wanted to mention that before I would forget. So let me go to OneNote. We were talking about examples. Okay. We were talking about this example here. So let me refresh your memory. I'm not going to read it again, but essentially we said we have a vehicle traveling at a certain speed, and then there's a tree here at the BPT of this sag vertical curve that has this grade, this entry grade minus 2.4%, and then we have an exit grade of 4%. And the length of the curve was 150 feet, although that was given, and the question was whether it was assuming it was reasonable to expect the driver to be able to stop before hitting the tree. Okay. So we started with this last week. So essentially what we said initially is we need to figure out which equation we have to use. And I mentioned the other day that I like to start with this one because there's a real linear relationship between L and S. That doesn't mean this would be the right equation, but that's what I did the other day. I assume that S is greater than L, and that's an assumption we have to check. Okay. And so since we know L is given as 150 feet, so we are given G1 and G2, which essentially determines the A. Then I solved from this equation for S, and it gave me a value of 146.24 feet. That's the side distance that this 100 feet vertical curve is going to provide. Okay. For the conditions which standard provides of 2 feet the height of the headlights and 1 degree the angle of divergence of the light. So for those conditions, this curve will provide 146.24 feet. And then you go on and go back to your assumption. Is this the right assumption? You can see that the S that you estimated from the equation compared to the L, you see that S is not greater than L. That's the assumption we made. Therefore, that assumption was wrong. Nothing wrong with the analysis, but the assumption was wrong. So you have to go back and say, well, this assumption is wrong, so this must be true. And I think that that's when we stop because I ran out of time the other day. So essentially you go back to the drawing board and say, no, this is the correct equation to use. So now I'm going to solve for S from this equation, and you can see this is a quadratic expression. It has S in 2 places, so it's more challenging, but it's not that difficult anyway. So if you put everything on one side, that equation simplifies to this. I'm not going to go over the algebra. Okay? You just need to replace the A and the L by its values, which is what I did here. So you can see a quadratic expression, you can get, it will have 2 roots. One of those would be the correct value. It's one of the things you have to get used to pick up the reasonable value. And then notice that in here, the reasonable value would be the one that's positive, because if I put minus in here, this value below the square root is greater than this other value. So I will get something negative, which makes no sense. So that's why I picked the root it makes sense. And now you see that the S is less than the 150 feet of a curve, which is what makes this relationship the correct one. That was the assumption for this equation. So now we know what the S is. And notice that in this particular example, it really makes no practical difference, but this is the right equation to use. Okay. So this where I stopped the other day, and I said we will finish next class. So the question we still need to answer is it reasonable to expect the driver to be able to stop? And I don't know, I rewrote this earlier and I still wrote it wrong. It's a question, so is it? Okay, is it reasonable for this? So we have to link this side distance, which is the supply side distance by the curve, with the stopping side distance, which is the demand side distance you have to be able to stop. Okay. So we have an equation for stopping side distance, this same equation that we have been using throughout the class. We're going to make a simplification here. So we have the initial speed times the perception reaction time plus v squared over 2g, the friction plus the grade. And the problem here for vertical curves comes into play in this value of g. The problem is that the grade in a vertical curve is not constant, right? It's changing constantly. So what grade do we use? You see here, I have a value that is very close to 0. And the reason is because I took the average value of the grade. Okay? So in this case, I took minus 2.4 divided by 4. Sorry, minus 2.4 plus 4 is the, in this case, we're not taking a difference. We take the grades, the two grades with their sign, and we add them up and divide by 2. And then I get, in this case, the difference. So this value is 1.6 divided by 2 is 0.8%. So that's why I put here 0.008%. It's less than 1%. Okay, so 0.008. That corresponds to 0.8%. And that's a simplification. Essentially, what would we have to do if we don't make this simplification to get the stopping side distance? Can anybody guess what we would need to do?
Integration.
Sorry?
Integration.
I heard calculation, but I didn't hear anything. What else? Can you?
I think he's saying integration.
Integration. Okay. Integration. Perfect. So yeah, integration. That's what you need to do, right? Because the grade is changing constantly, so you have to take very small steps, and with initial speed compute the exit speed. So you do a very small integrations numerically, but the reality is that it's not worth it. Not worth it because, if you knew the friction factor perfectly, but this is something that comes from the policy. So, but we still need to put something in here. Some people would take the maximum, but most of the time, the average grade will give you a reasonable value. And it's not so conservative like taking the most adverse grade. Okay? So in this case, I could have used, right, the minus 2.4%. If I have put here minus 0.0224, that would have resulted in a longer side distance. But the reality is that you're not going to be driving on a minus 2.4% grade all the time. It's just at the beginning, and then immediately, you're going to be transitioning. So that's too conservative. So this is what most people use. And let's stick with this value, taking the average for the problems in the class, just to be consistent. Okay, so that's the only difference. The rest is what we have done to compute the stopping side distance. So I got a value, I plug in values, the speed, converted in feet per second, the perception reaction time, and again, the speed, the friction factor, according to what the standard, remember, is defined as A over G. But A is not the acceleration, it's the acceleration on a level grade. So I got this value of 194.44 feet. So So what? That's the value, that's what I need to stop the vehicle, but this is what the curve provides. So this is the demand for side distance, this is supply for side distance. So with these two values, you can already answer the question. I don't think, or if I did the other day, I think I went too fast over this. So this is my demand for side distance, this is supply. Whenever you see that you have more demand than the supply of something, then the supply is inadequate. Right? So in this case, what this says is it's not reasonable to expect the driver to be able to stop, because by the time it sees it at 146.17 feet, that driver requires a longer distance to stop. So that tells you that it's not reasonable for this driver to stop. Is this clear?
Yeah.
Yeah. Okay. Thanks. It's great. Now I can see you when you answer, when you talk. Okay, perfect. There are alternative ways. Let me mention the two alternative ways that you can approach this. You can make the stopping side distance equal to the supply side distance. This is what I'm doing here. And then you solve for at what speed that side distance will allow you to drive safely. Right? So notice that I'm saying, I don't know what the speed is. Let me solve for speed. So I will have to solve a quadratic expression again. Okay. And then I compare that speed, which is the speed at which that curve allows me to drive safely, with the design speed. Again, if you can drive at a speed that is larger than design speed, then that's a safe condition. If the curve allows you to drive at a speed that is lower than the design speed, then it's not safe to drive at the design speed. And in this case, we're not answering whether it's safe or not, but it's whether it's reasonable to expect the driver to be able to stop or not. But safe is the driver would be able to stop, and unsafe would be the opposite. Okay. Can you see that this is an alternative way to answer the same thing? And there's a third way, and I like to explain this one mostly because it relates to what the notation in your textbook. If you look at your equations in your textbook, they all have, when they provide these equations here, they put an L sub m. And the m is for minimum length of the curve. So let me go back here and tell you why that is. So in this problem, we were given the design speed. So at that design speed, we can compute the stopping side distance like we just did a few minutes ago. And with that stopping side distance, let me just go back, not this value, it's not this. In here, we made this stopping side distance equal to the supply side distance. And what I'm saying now is that this stopping side distance that we computed from this equation, right? That value, I'm going to make it equal to S. Okay? Which is the side distance supplied by the curve, which I'm assuming I don't know. So I make that equality. And I solve now for L from the equations. And again, I still need to find out which case is correct, right? But the important thing is that I solve for what the minimum length of a curve would be, and I have a given length. Remember, we started the problem here in this particular example, the curve is 150 feet long. So if I get that for that design speed, the minimum length of a curve that I should have to drive at that design speed is greater than the length of the curve that I have, that means that my curve is unsafe, right? I should have a minimum length of, let's say, 200 meters, but my curve has only 150. So minimum means minimum, right? So if you have something less than the minimum, then that's not good. So in this case, it's unsafe. Excuse me. And if you get a length that, a minimum length that is less than the actual length you have, then that would be safe. So either way, just don't get confused with which one of these is the correct answer. And don't forget, in here, you would have to assume one of the two equations you have available and figure out which one is correct. And again, you do the same. In one case, you solve for S when you know L, and then you compare the values, or in other cases, like in this one, you solve for L when you assume you know S. There are different ways of looking at exactly the same problem. So I'm just trying to give you all the alternatives that you may have. Okay, so let me just take the next example. Is basically the same thing as this one. The only thing that I did is I changed the grades, 3 and minus 3.4%, but notice that they still add up to 6.4%. And I mean, the absolute, the algebraic difference in grade is still 6.4% in absolute value. And the length is still 150 feet. So it's basically almost an identical problem, except just the average grade would be slightly different, but that's it. So if you do the same problem now for a crest vertical curve, then you would have to go and look into the equations for crest vertical curves. So make sure that you pick the right equation, right? So right now we're having tests that are open notes, open books. So there's no excuse for picking the wrong equation, okay? So just make sure you get the right one. So you make an assumption, S less than L or S greater than L. So in this case, I assume this one, okay? And like I said before, probably would have been better to start with this one, but in this case, I'm just trying to make the point that if you make the wrong assumption, you can always go back to the other equation and get the right equation. So let's see, I made this assumption. I substitute the value of A, which is the absolute value of the difference, the absolute value of the algebraic difference in grades. So I get the 6.4%. Also, be very careful, these equations, remember, in these equations, A is in percent, and the L and S are in whatever distance you are working, either in feet or in meters. I mean, again, you have to be careful. Pick the equation that corresponds to the system of units you're using. This value, 2,158, depends on the system of units you're using. Okay, so it's just a matter of substituting L and A. I got a value for S, and then I check, is that value for S, the value that you just obtained, less than the length that you're using in that equation? No, it's not, it's larger, right? So it was the wrong assumption. So wrong assumption means this one over here. So we have to go back and use the other equation that you have available in your notes, which is this one, which corresponds for S greater than L. And again, I solve for S, and I get a value that is indeed greater than the value of L. And once again, I'm going to solve the problem the same way. I'm going to plug the value of the average grade, which in this case, minus 0.2%, or minus 0.002. And that's why you are going to see that value over here. And the rest is the same thing that we did before. Now I get 196.88 feet. And notice that for the sag, for the crest vertical curve, what we get is now the stop inside distance that I get from this equation is 197 feet, which is less than what is applied by the curve. So for a crest vertical curve, it is reasonable to expect the driver to be able to stop. For a sag, it was the opposite conclusion. Okay. Any questions about that? That's why you have to check every problem, because you cannot guess it from what you, from your sketch here.
I have a quick question.
Yeah.
Do you think you could go over how we pick the S equations, the side distance equation?
Okay, it's very simple. Let me just go to my notes. You're going to have, let me see where they are. Trying to, here. You have this. So, if in a problem I tell you the height of the objects, or, well, if I tell you the height of the objects, and this is just for, actually I have it for all of them. So if I either give you these two heights, or I give you this other height and the angle beta, you just pick these equations. This for crest vertical curves, these two, and this for sags. The problems that I just explained, they have units on them. So you have to go and either pick, if you have, for the problem with crest vertical curves, you would pick these two equations or these two equations. Those problems we were working in SI units, right? So that's why for crest vertical curves you would pick. Okay, hold on. Were we working in meters, or I thought it was? Hold on a second. Let me check something. Hope I'm not wrong. Why did I put feet there? Okay. Hold on a second. Okay, yeah. There's nothing wrong that picking the wrong number of equations when you're complaining about that. Okay, so we were working in US customer units. For some reason, I got confused while I was reading this. We're working in the US customer units. That's why you saw that value 2,158, right? That because I picked these equations for the units that I'm using. So you either pick these two equations or these two equations. That's it, it's that simple. So that's why in this problem, this is the first equation that I showed you there, and this is the second equation. And for the first problem, which is a sag vertical curve, notice the two equations that I pick. They have 400 and 3.5 in there. So let me look. For sags, I have a slide with sag vertical curves where you have for the US customer units, 400 and 3.5. So that's why I picked these equations. If I give you a problem with the length in meters or the side distance in meters and the speed in kilometers per hour, then use these equations. These for sags or these two for crest vertical curves. So it's just a matter of picking the right equations from there. So did I answer your question?
Yeah, thank you.
Okay. I have to find a way, I look down because I'm looking at you, but I'm not looking at anything else, but I need to find another place where to put that computer. Okay, so let me move to the next example then. And you can see this similar to what you had the other day in the midterm, and actually was part of a previous midterm. So this would be typical of those midterms. I give you an alignment and I start asking questions. I give you some information and ask questions about them, right? So in this case, I'm asking you, given this information, and this was from part of a bigger problem, so some of it may not be relevant. Although I think everything is relevant. Well, probably the length of the horizontal curve is not. So it says here, determine the elevation of a point P with a station equal to 3 plus 60. And everything is given in meters, so here one station is equal to 100 meters. So it's just elevation of a given point, and it's not even shown. I'm not even showing you here where that point would be. But you start getting some pointers in here. This station 360 is greater than the station of PC1, so I know the point would be somewhere over here, beyond that point. And in fact, if I see a station of VPC1, which is this point here, the beginning of the curve, I see that that station is 3 plus 20, so still point P would be somewhere beyond that point. So it would be either in this vertical curve or on this tangent. Okay, and then I'm also told that that vertical curve is 130 meters long. So if I add 320.35 meters, which is the station of this point, plus 130, that's what I have in here. And I get that the station of the end of the curve, or the VPT1, is 450.35 meters. Okay. So the only reason why I'm doing this, because in this type of problem, hey, I want the elevation of a point that is somewhere over here. First, you need to find out, is that point on a vertical curve or on a tangent? If it's on a tangent, if it's somewhere over here, you would have to figure out the information given, if any, about this grade, and you have to have some elevation of some other point. And that's why I added in one small section in the midterm, I added in one of the questions that, because you should be able to know that, because that goes to the definition of grade and knowing about a point. But in this example, we're trying to exercise vertical curves, so you can bet that this point P falls somewhere here in the curve. And the reason I know that's true is because when you look at the station of P, 360, that station, which I wrote here, that station falls between the beginning of a curve, that's given, and the end of a curve, which we just computed here. Okay, so because of that, I can say that P is inside that vertical curve. And therefore, in order to compute its elevation, sorry, I'm moving things so much, but in OneNote I don't have the, so in order to compute the elevation, let's say P falls somewhere over here. Let's say this is P. I don't know where that point is, but let me call this P. I'm gonna, in order to compute the elevation of that point, I'm gonna need to use the vertical curve equation. And let me make a graph. So let me exaggerate this. We have one grade, then we have the other grade, and then we have a vertical curve. Something like that, right? So let's say this is my point P, and I want to get the elevation of that point. So what I'm going to do, let me move the beginning there for convenience. We're going to define a local system with X there and with C over here. And then we want to get the value of C corresponding to that point P. And we're going to do that as a function of the location of that point relative to the beginning of the curve. So that value of X, I can get it from the station of the point P, which I know, and the station of the beginning of the curve, because I know it. So that difference in stationing gives me that distance, XP. With that distance, I will be using the vertical curve equation to figure out this difference in elevation, which I will add to the elevation of this point, and that's it, problem solved. That's all we're doing here. Is that clear? Do I need to repeat what I just said? Okay, I assume I don't need to do it. So this is all I'm using. I told you the other day, this equation I remember. I find it easy to remember. you can have it in your notes. So the C value that I'm customizing it with P just to indicate is the elevation of that point P relative to the beginning of the curve is G2 minus G1 divided by 12 times X squared plus the G1 times X, okay? So I put X sub P on there. So first, let's determine the X sub P, the station of P, the station of this point here, minus the station of this other point. I have the two values. Both of them were given to us. So the distance is 39.65 meters. And then I plug that value into the equation. I get a value of 0.03 meters. So it's just 3 centimeters, less than 1 inch, right? So something like that from the beginning of the curve. So even though we are quite a distance already inside the curve, but the difference elevation between those 2 points is very small. And then I add that elevation, the difference in elevation, to the elevation of the VPC, which is also given, right? So it's given over here. And that's it. Is it simple enough? Not hearing anything, I assume it's very simple. Okay. The fourth problem is basically the same thing. Again, I'd like to give you variations of the same thing just to, well, it's slightly different. And this problem, is, you can see it's basically the same problem. I just ask a different question. Find the elevation of the highest point on the vertical curve. And the other day I gave you some equations to figure out what the highest point is. Let me just stick with this. Highest point is the point where you reach the maximum elevation. If it were a sag vertical curve, I would ask, what's the location of the lowest point? As long as you change grades. If you don't change grades, then you don't have, you will not have to do this, okay? So if the road changes grade on that vertical curve, at some point it's going to reach a maximum or a minimum. So in this case, we will reach a maximum because we go from a positive grade to a negative grade. So we take our quadratic equation, and we just take the derivative of that, of C with respect to X, and that gives me a condition for a maximum. So you can see I will solve from this expression for X is minus G1 L over G2 minus G1. I plug in the values of the grades and the length of a curve, which is given here. And I get that the maximum, the point of maximum elevation is located at 21.67 meters from the beginning of the curve. Then once I have that value, I plug it back into my quadratic expression, and that will give me the location of the maximum. Okay. And that's it. Now I add that elevation to the elevation of VPC, and then I get the elevation of the highest point. And I don't have many more questions to ask. Things are not much more difficult than this. Okay? And that's basically it for these examples. Just to finish, so finally we are finishing with these notes. Let's see a few more things. There's another set of two equations, and in some cases you have, like this is the on University Avenue, right? So sometimes you have underpasses, and this is not a good example because actually you can see pretty far ahead in this case. But in roads with more curvature, and when you have an underpass, you may not be able to see on the other side of the road. And actually you can see it here. You may be here, and the bridge will limit you how far ahead you can see. Okay? And you have exactly the same problem that we have seen for crests and sags. In this case, the problem would be on sags only. Again, you have a set of two equations. One applies for when the length S is less than the length L, and the other one for S greater than L. okay? And that doesn't depend on the units. It depends on the values of H1 and H2. And that depends whether you give them in feet or in meters. So depending on whether you're using feet or meters here, then you end up with two different sets of equations. These ones, don't worry about in the next class. I'm not going to give you a problem with this. I'm not going to use them. But just be aware that you have this other situation as well. So just to finish, this is how a typical plan and profile looks like. I have had this slide for years, and today I look it up, and this in Kauai I think I have someone from Kauai, so north of Kauai, and the reason why I got interested was on this. Can anybody tell me what that value is? I mean, what does it mean? No, I can't read the value, but oops. Let me see if I can make it bigger there. What is that?
Oh, that's the direction due north.
Yeah, it's the azimuth. Yeah, perfect. This is the azimuth. So that tells you the road is going, it's between 270 and 360. It's pointing northwest, right? So that told me that road, even though I'm not looking at anything else in the plan, it's telling me that thing that I see pointing to my right, really, when I put it on a map, it's pointing kind of like in the opposite direction, right? Just to get an idea, but they have to do these things, right? They have to put the road from, this is the horizontal alignment, this is the vertical alignment. So this is how a typical plan and profile would look like. So you can see the numbers now, the 580 plus 00. Now you know what these things mean, right? So that's the stationing that they're putting there on a baseline, which in this case, that baseline is the center line of the road. Then you see they are putting, here we have a horizontal curve, and they're giving you what the station of that curve is. And notice that when I'm telling you work with 2 decimals, that's what appears in the plans and profiles, right? Or with that precision. Then you have the delta of a curve. Now you know what the delta is. It's the deflection angle or the central angle of a curve. That's the delta that you see there. That's the radius of this curve, is 630 feet. The tangent, the chord, and the length of a curve, okay? So notice that sometimes the notation changes slightly, but now you know what these things mean. So you can read this stuff relatively easily. You also have here the vertical alignment. So in this case, on this length, which is about 580 to, we have about 20 stations, at least from here to there. And so the same length, you see it here, right? So in that same length that we have one horizontal curve, we have 2 vertical curves. This is the design grade of the road. And this is the natural terrain on the center line. So this will come from a survey, and this is where you are putting you're making the decision over here, at least on the center line, I'm gonna have to cut this. Over here, all this will need to be filled. Okay? So these are the trade-offs. These are the things, like in this class, I'm telling you, oh, we have a vertical curve. In practice, this is what you are trying to, you have a trade-off of how much you cut and how much you fill. But remember, we're looking things at one vertical surface, which is that center line. The road has a width, so I'll show you in a minute what else we have to consider. But for these curves, you can see again, it's telling me where the station of a curve starts. So this is the beginning, the VPC. We have the VPC of this vertical curve at station 591 plus 00, and it ends at 599 plus 00. So it's 800 feet long. And the enter grade was 417 and the exit grade 6.77. So this is negative, that's positive. And same thing here, again, this curve would have a certain length that is given here, 700 feet. And you can see they have picked pretty round values, right? So from the equations that we were discussing earlier, perhaps you get, oh, this curve should be 553.2. Well, the designer chose 700, something larger than the minimum. If you are trying to be very economical, perhaps you pick exactly the minimum, right? Because the more you can adjust to the terrain, the better it is for cost. You reduce cost. The uglier the road looks like. So those are the trade-offs, the things that you really consider when you're designing roads. In what I'm used, remember, most of my practice on this was from my country back in Argentina, from where I was born. In that case, we would have, in addition to all these things, we would have a lot of boxes in here with information. And that information included things like, well, how long each culvert would be. So we put information for computing things. So because, you know, the length of a culvert will depend on whether the culvert crosses the road like that or it crosses like that, right? So this one, this situation, this culvert would be much longer than that one, even though it's crossing the same road. So it depends on how the stream crosses the road and things like that. So even if you hate roads or anything I'm saying, in practice, a lot of things you're going to be doing is cost estimation, right? So knowing how long and how much volume of concrete you need for a culvert, or if it's a metallic culvert, how much of that you're going to have to pay for, it's important. The same thing of how much earth you're going to move, that influences the cost of the road. So even if you don't care about designing a highway, it's important for you to understand some of these things, because some of you will end up working in highway engineering. So I hope. Let's see. I think that's it for that one. I added this today, and I'm not sure if I upgraded the notes, but I will do it, because this was one of the items that was the most expensive ones, at least for new design of roads. For, you know, when you're rehabilitating the road, the most important thing typically is the payment cost. But when you're designing a new road, you will have to, like in this road here, you will go from a section like this that is completely in fill. You can see this, all this section, you will have to fill it to be able to build the road at that level. In here, we are still cutting the road, filling the road. In here, we are still completely filling it. But from this point on, part of the section is being cut, right? So this want to be cut, and here we're filling. In here, we transition already to a complete cut. So you can see over here, all these cross sections have padding cut and padding fill. And after that, we are completely cutting. Okay. So part of the trade-offs is putting the road so that the road goes up and down, but you don't want them to make them very steep, so you have the freedom of making it go up and down, but also left and right. And one of the things we're trying to minimize at all times is how much earth we're going to need to move. And one of the things you need to do when you work in highway design is computing that and estimate that volume. We're not going to consider this in this class. I stole this slide from a surveying book. Okay, if you're interested, pick one of these, a book like this, and you can learn more about that. It's a lot of geometry, but essentially what you end up doing is computing cross sections. For example, you would compute what the area of this section is, and then the area of that section. And with those areas and the length between them, using different equations, you compute the volume. So one would be simply taking the average of the two areas and multiplying by L. That has an error. There's another equation that considers the area of a section in the middle. Again, I'm not going to go over that, but you will compute the volume between every pair of cross sections you consider. And with that, you're going to compute a cumulative diagram that helps you to determine how you're going to move the Earth. It's not just about how much Earth you're going to move, also how you're going to move it, because the cost depends on the length that you have to move a certain amount of material. So it's a very interesting topic. Unfortunately, we don't have enough time in this class to cover this in detail. I hope you guys understand and see it as interesting like as I do it. But going to what I was asked the other day about how you put things in the field, one of the first things you see, it says center line stake. One of the first things when you do a construction of the road, you're going to have to stake the road on the natural terrain, and from there, they're going to start moving earth and things like that. They need to have a reference. So you need to materialize the road in the field, particularly when you're in the middle of nowhere. Okay, I'm talking too much. And any questions about this? No. Okay. This is just to indicate things that we're not going to cover, and we have not covered, and I'm not going to cover. Particularly on two-lane highways, you care about not just the stop inside distance, you also care about the pass inside distance. This is from AASHTO. They have a very simplified model. Some of the things we have covered in class about vehicles going in opposite directions, it's a little bit more accurate. But we're not going to cover this. Also, when you design curves, something we haven't talked about, but it's the cross section. Actually, you have to widen it to account for the fact that the vehicles will have off tracking. You know, the path of the front wheels of a truck will not be the same that the path of the rear wheels, and therefore the width of the truck is as if it were wider, right? So you need a wider cross section for that vehicle to maneuver. Okay, and that becomes more challenging when you have very small radius of curvature. So for intersection design, there are templates for the type of tracks to figure out how those tracks are going to be able to move. But on highway design, you will provide, like you can see here, a widening on curves. We're not going to talk about that either. And then I have a bunch of slides that you can read about things that are convenient. These are guidelines of things that you should try to avoid. Remember when we started this class was this set of notes, I showed you a road and I said, oh, that looks ugly. Well, that road was doing something like this, right? So when you have dips in the road, just to try to adjust to the terrain, whenever you can, try to avoid these things and put something like that. Again, it depends on cost, right? And design speeds and things like this. This is another example. I have seen this in practice. It's awful, right? So just they're putting some culverts in here and then they adjusted the road like that. Unless you have very gradual curvature, this looks ugly, particularly if in plan view it looks like this, because then you can see the road from the side. So it's not good. Okay. So similar thing to what I discussed before. And then you have other things, combinations that are not convenient that you can try to avoid. I'm pretty sure you're going to drive and see a lot of these things anyway, but you don't want things like this, where part of the road gets out of sight for just a little bit, because then you may fall into a false sense of security, right? So if I approach this road on a curve and I come to something like this and I think, oh, I can see the road ahead. And I tell you, it happened to me once, and I was passing someone, and then someone else appeared over here. Scary situation. Okay. Anyway, so you can look at those things on your own. And that's it for highway geometric design.